Okay, today it is time for the washer method in finding volume of solids of revolution. So before we get into the washer method, let's go ahead and do a warm-up, so you can pause me if you'd like. But we are being asked to evaluate the integral that gives us the volume when we take this two-dimensional shape formed by y equals 4 minus x squared over 4 and y equals 2, and we revolve it around the horizontal axis of y equaling 2. Okay, so this is the axis of revolution. So if we kind of imagine taking the shaded region and revolving it, we can envision having kind of that symmetry taking place, but we're going 360 degrees, so we have this rounded figure after we revolve. Okay, so what we have to do first is we have to define the height of the representative rectangle. So we can't just use this function to represent the height, or else it would go all the way to the x-axis. So in yesterday's notes, we talked about defining the radius of each representative disk. So we see that we're going to have to take our upper function, which is 4 minus x squared over 4, and we need to subtract our bottom function, our lower function, which is just y equals 2. Notice both of these functions are written in terms of y, which is perpendicular to that horizontal x-axis of revolution. So when I clean things up a little bit, we have 2 minus x squared over 4. That is going to be the radius of each disk, and you can kind of see those disks that I drew in blue. So now when we find the volume, we always have our pi out front because we're using pi r squared kind of as our reference. And we are going to go from, when they give us diagrams, it's really nice, -3 to 3, and usually they have to establish that. And then after that, we are going to take our radius function, which is 2 minus x squared over 4. We are going to square it, and we are integrating with respect to x. Okay, now you can go ahead and expand that because we do, with integration, want to use power rule. So we have pi times the integral from -3 to 3, and when we expand the binomial being squared, we get 4, and then minus x squared, and then we have plus 1/16 x to the 4th. Okay, I'm taking 2 minus x squared over 4 times 2 minus x squared over 4, so double distributing. Okay, now at this point, let's go ahead and just do the integration because it is a warm-up. So we have pi, and we have 4x minus 1/3 x cubed, and then plus, 16 times 5 is 80, so 1 over 80 x to the 5th, and we have to evaluate that from -3 to 3. Okay, now at this point, you could go ahead and use the integrate feature on your calculator, and it will give you a decimal, but it's a non-rounded decimal, so you can go back to your home screen and convert it back to a fraction, back to a rational number. Okay, so when you do this, either way, by hand or by your calculator, okay, kind of ignore the pi until the very end, so do not put pi into your y equals, and you are going to have 483 pi over 40. So 483 over 40 is what your calculator would give you looking at the integral portion of the problem. So that's approximately 37.93 units cubed. So this is the volume. Remember, we're working with volume of a three-dimensional solid. Think, how much water would it hold? How much material would it hold? Okay, so now we are going to take it a step further and look at how are we going to find the volume of something that looks like maybe a donut, okay, where there's a hole in the middle, where that icing is taken out of the middle, and we only want to look at the cake portion. So the washer method uses the same concepts as what we just went through in the warm-up, but there's just kind of one additional kind of function we have to pay attention to. So let's look at some quick notes. It says the washer method is an extension of the disk method. The only difference is the representative disks have holes in them. So when representative disks that we repeat over and over and over have holes, we don't call those disks anymore. We call those washers. Okay. So, in order to find the area of a representative washer, we must determine the function that defines the length of little r. That is going to be used to describe the inner radius. Okay, so you can see on our donut shape here, this is little r. Okay, but then we also have to establish what function, so what function defines little r, this curve right here. But then what function defines big R, which is the outer radius, the radius of the kind of larger function. Okay, so big R would be this, and we can see that, okay, the outer function I've kind of highlighted in blue. So the idea is we have to find the area of the representative washers, and then we'll repeat those with minimal width for the span of the solid. So what are we going to do? Okay, we have to find the area of the large circle first. And then we have to go ahead and use that smaller radius to find the area of your inner circle. And so when we cut out or eliminate the green, okay, we are left with this red portion, which is the area of the washer that we need to use to then find the volume of the related solid. Okay, so to find the volume of a solid of revolution, we must integrate the area of the representative washer. And we mentioned this yesterday, okay, that just like when we would find the derivative of position, that was velocity, and the derivative of velocity was acceleration. Okay, the same thing kind of goes with integration. The integral of a function gives us the area, and then the integral of the area will give us the volume. Okay, so what are we going to use when we have a hole in the middle of our solid? Okay, we are going to use volume equals pi. We're still using pi r squared, okay, but we have to find the area of the big circle and subtract the area of the small circle. So in this case, we are going to take the function that defines the big circle, okay, and you could picture a pi right next to it, and we have to subtract the function that defines the radius of the small circle and square it. So really we're taking the area of a large circle minus the area of the small circle, but we're integrating it to get us volume. Okay, so what we can really think of is that when we have an integral that involves an inner radius, okay, that's representing the volume of the whole. Okay, so when we integrate the inner radius using pi r squared, okay, we are really finding the volume of the whole. So if we kind of sketch in this picture here, we're trying to do the mirror image, okay, the inner radius, which is little r, we're really finding the volume of this hole here. This is the hole. Okay, so then we subtract that from the integral that involves the outer radius, which would be like what we did yesterday. If you look at this picture right here and pretend there is no hole and it's filled in with some sort of material, okay, we're going to take that volume, subtract what we did here with the inner radius, and that is going to give us the volume of what remains of the solid with the hole. So now we're going to do some example problems. You're going to see the similarity from what we did yesterday. So hang with me. If you want to pause, try and fast forward, that's fine as well. Okay, so we are going to find the volume of the solid formed by revolving the region that's bound by the graphs of y equals square root of x and y equals x squared about the x-axis. Okay, so we are revolving about the x-axis. So we're kind of envisioning, draw our flower petal down here as well. Kind of like a bowl, I guess you would say. Okay, we're going to rotate that flower petal so you can see that the hole is going to take place kind of in this region right here. So think of a bowl. So in order to do this, okay, we have to establish kind of what defines the hole. The hole is defined by the lower function, and then what defines kind of the outermost part of the solid, that is going to be defined by the upper function. So we have to integrate by taking pi times the integral. Now, when we look on the x-axis, we are going from 0 to 1. And our big radius is defined by the square root of x. You can see it's labeled, but we also know what our graphs look like. Squared. And then we have to take minus x squared squared. That is defining that inner radius. And we're integrating with respect to x. So now from here we have pi times the integral 0 to 1, the square of a square root breaks out what's underneath, and then we have x to the 4th dx. Now we can go ahead and integrate. So we have 1/2 x squared minus 1/5 x to the 5th. And we're going from 0 to 1. I love when 0 is there with all the x's. So we have pi times, let's see, 1/2 minus 1/5. I love taking 1 to a power. And then we have subtracting. When we evaluate for 0, everything is 0. So when I take 1/2 minus 1/5, I get 3/10. So I end up having 3 pi over 10 units cubed. That is the volume of the material that is creating, I'm going to call it the bowl, okay, or the cup. So what is this? The volume is not that much. It's very thin, and you can kind of see from the picture that it is 0.942 units cubed. Okay, so that's what I would kind of call like a basic washer method type problem. Okay, so now we are going to go ahead and continue on. On question 5, okay, we see that this is kind of a story problem. The manufacturer drills a hole through the center of a metal sphere that has a radius of 5 inches. Okay, they do give us these nice diagrams that ultimately give us the equation of the sphere, the function of the sphere. But just as a reminder, if you would see this, you know, okay, the equation, assuming it's from the origin. So we know that a sphere is related to revolving a circle around an axis. And so what's the equation for a circle? It would be x squared plus y squared equals radius squared. So 25, 5 squared is 25. Okay, so then if we are looking at revolving around this x-axis, then we would need to solve for y. So we would get y by itself by seeing y is plus or minus the square root of 25 minus x squared. But because we're in that upper region, we can ignore the negative root. So that is how they came up with the function square root of 25 minus x squared as the definition of the outer function. Okay, but then it says they drill a hole that the hole always has a radius of 3. Okay, so what shape is that hole going to be? It's really going to be a cylinder. Now, what does a cylinder relate to two-dimensionally? A rectangle being revolved around the axis. So kind of what makes up a rectangle? A horizontal or a vertical linear function. So in this case, you can see if we're going from the x-axis, y equals 3 is the function that's going to define that cylinder. Okay, but now if you look at the picture, and I got tricked on this when I was going through the lesson, okay, they show on the picture it would be easy to carry the sphere out all the way to 5 as your limits of integration, but it goes from -4 to 4. They're cutting it off at those points. Okay, so if we're going to go ahead and find the volume of the solid with the hole, we are going from -4 to 4, and we need to take the large radius, which, look at the top of your representative rectangle, that is going to be the square root of 25 minus x squared, and we are going to square that, and then we have to subtract the area of the smaller circle, which is going to be just defined by y equals 3, and we're still going horizontally, so we have dx. Okay, so if we clean some things up, we have -4 to 4, 25 minus x squared, because those roots and square cancel out, and then -9 dx. Combine things together, pi from -4 to 4, and I have 16 minus x squared dx. So at this point, okay, I kind of mentioned this earlier, you can put this into your graphing calculator, find the integral, and then tack a pi in front of it. But you always want to go back to your calculator math, or just your calculation screen, to see if you can convert it back to a rational function. Okay, so you end up getting, if you convert it back to a rational function, 256 over 3 times pi. So the volume, okay, is going to be 256 pi over 3, which is approximately, oops, I didn't do that approximation, so you can go ahead and do that at your desk, but that is our answer. Okay, that is the volume of a sphere with a cylindrical hole cut through the middle. Okay, and now we have one more question that we are going to do on this note sheet, and we need to look at what happens when we are going to use horizontal related rectangles. So we are going to find the volume of a solid formed by revolving the region bound by this parabola, y equals x squared plus 1, and then we have these horizontal and vertical lines, y equals 0, and then x equals 0, and x equals 1. And you cannot skip over the fact that we are revolving around the y-axis. So now on these problems, you have to be very careful, because if you look at this first representative rectangle here, we see, okay, that it goes all the way to the y-axis. But then if you look at this representative rectangle here, we see that the height of the rectangle is not just defined by this function x equals 1. It's defined by x equals 1 and this parabola right here. Okay, so this is a two-part integral that we're going to have to do. So if we look at this first part here, if we want to consider finding the volume, okay, we're really just going to reflect, and what shape is this going to be? This is going to be a sphere, but is it going to have a hole in it? No, it's not, okay, because the entire two-dimensional rectangle is being rotated around, so there is going to be no hole on this bottom part. So this is going back to the disk method. So we have to find this integral. I'm going to call this like integral 1, okay? And what are we going to do? We're going to do pi, and we are going off of the dimensions on the y-axis, so from 0 to 1. and we need to use our functions in terms of x. So we are going, our radius is going to constantly be defined by x equals 1, and we are integrating with respect to y. Okay. Then what are we going to do with this? We are going to have to add it to whatever we get when we look at the upper solid separately. Okay, so if we look at solid 2, we see that if we rotate it about the y-axis, okay, now we have kind of this sphere that has this parabola-like hole that is cut out of it. Okay, so this is going to use the washer method. So the green is going to use washers. So I have, okay, pi from not 0 to 1. Now I need to look at my 1 to 2. But it would be tempting to, okay, we can go ahead and use x equals 1 again because that is actually my outer function. So I have 1 squared. But what's my inner function? It would be tempting to use x squared plus 1. But if we are rotating about the y-axis, what do we have to do? We have to rewrite this in terms of x because we have to have y's in our integral. So if I'm working with y equals x squared plus 1, I need to move my 1 over, and then I need to square root. Okay, and we could have the plus or minus out front, but again, we're only going to deal with that positive section there. So now we can go back to our integral and we can say, okay, now that we have it written in terms of y, that's our inner radius, our little r, dy. Okay, so this is two separate integrals. There's no way around it because the solid form has to be coming from revolving around the y-axis. So if I look at the purple, integral number 1, this is a nice easy integral. So I have pi, and when I integrate 1, I get y, and I need to integrate that from 0 to 1. Okay, and then I'm going to add that to, well, I've got to clean some things up in the green, so I'm not ready to integrate there. So 1 squared is 1 minus the square root cancels with the square, dy. Okay, and then in purple, I can keep moving along. So I have pi times, let's see, 1 minus 0. And then in the green, I'm going to combine some more things. So I have pi, still not going to integrate, but using proper notation. That's very important. And so I have 1 plus 1, really, because of the double negative, minus y. Now that's going to be ready to go. Okay, so then in purple, I'm finally kind of to the end there. 1 times pi is pi. But then with my green function, I have pi, and then 2, when I integrate that, I get 2y minus 1/2 y squared, and I'm taking that from 1 to 2. Okay, now from here, I can go ahead and copy down this purple pi, and then I have plus pi times 2 times 2 is 4, 2 squared is 4 times 1/2, so minus 2. So that's evaluating for the upper limit of integration. And then when I input a 1, I get 2 minus 1/2. Okay, then I need to simplify inside. So I get pi plus pi times 2 minus 3/2 or 1.5. So I have pi plus 1/2 pi. So I get 3/2 pi, or 3 pi over 2 units cubed is the volume of the entire solid. But again, this was a 2-part integral. Okay, so that is the notes for today. Please make sure you are keeping up and really doing those practice problems. Utilize the solutions that are on the internet, but make sure you understand what is happening. It does you no good to just copy. We're trying to master a topic. Tomorrow will be kind of a day of mastery as well. And please make sure you're letting me know if you have any questions. I am here to help.